Welcome to our demand forecasting project series. We have already seen how to clean the data and how we have saved by handling the missing values. Yes. So let's move to the next stage of our project, which is feature engineering and visualization. Here, this notebook shows all the performance of feature engineering on petrol demand data. We'll keep all the 11 columns, will not drop because one and another will affect our target, which is demand order. So we'll keep all the columns because time series based forecasting is required here, and we generate time based features first, which is a important feature from the time base, which is date, and then we'll add some lags and rolling features like mean value of the particular columns, like 7 days, 14 days, like that. And then we'll check some ADF test, which is augmented Dickey Fuller test for a stationarity. Stationary means we have to understand whether all the historical values where there is a trends or seasonality or some same patterns are repeating or not. If it is some trends and stationarity is not there, means there is a seasonality, it is not a stationary, it is gone dynamic. Stationary means it is almost constant over the time, the mean value or the variance value of our data points. Okay, so let's perform the seasonal decomposition then. So how we can take care of the seasonal components, and then we'll plot with uh, the correlation factors, a partial as well as a fully. So through that we can test and check our visualization. Then we'll save the CSV for the next building the model. So this is our second stage, which is important for the project. So before that, we have last time we have cleaned the data set, that will upload it in our Colab. So we have already cleaned the petrol demand, that you can open it from here like this way. I already opened it. I'll show you in my content. I have already uploaded. So clean petrol demand. You can take the path of it by taking the copy path. Okay. And before that, we'll install the important packages, or what we call as libraries required for our this second stage. So to install, we use a PIP. Okay, this is a Python install packages install. We have to use all the models or the packages which is required, like a stats model. Models is required for statistical modeling, like a time series analysis. If you are want to make a AD Fuller test or a seasonal decomposition or some plotting ACF, PACF. So for that we are making use of statistical models. Through that we have a different ARIMA model that we'll see in the next stage. But this time we need for analyzing the stationarity as well as seasonal decomposition, we need a stats model. And matplotlib for this is a visualization. Okay, so for having the effective visualization, we use a matplotlib library, which is a rich library for a good visualization. And then pandas, you know already, that is for data analysis and manipulations. Okay, so just installing this hash, whatever I write, this is a comment, and I'm just installing through this. I already run, so I just rerun it. See, like this, it requirements get satisfied. It's already satisfied, so it is showing fast. If you are first time doing, it takes some few minutes. Okay, then we'll import the libraries which is required, like import pandas as PD. You know that. Similar way, visualization, import matplotlib.pyplot as PLT. As PLT is a shortcut name for matplotlib.pyplot. And from stats model, as I said, from the statistical model, we want time series analysis, that is .tsa, time series analysis. Stat tools, from that we are in the model stat tools. Through that we can import a AD Fuller. AD Fuller is a augmented Dickey Fuller test. Okay, so this is a root test mainly maintained for to check whether our data points, the historical data points, are they are stationary, means they are constants over time, whether our mean value or the variance value, or it is fluctuating, like there is some seasonality or a trend. That will check with the AD Fuller test. Okay, and then we can have some seasonal decomposition. Through that we can check seasonal decomposition. So how to take that from the library, that from stats models.tsa.seasonal import seasonal decompose, that is seasonal underscore decompose. So this is a parameter which is making our seasonal decomposition using moving averages. Okay, let's see that how to use it. First, we'll import those all libraries from statmodels.graphics.tsa plots just to make up plots with the visualization, like import plot ACF. Through plot ACF, we can have a lags on the horizontal and correlation on vertical axis. Means from the ACF, we can find the term of what we can say PDQ. Three terms will be there. P means we can say aggregated. Okay, and then we have a differencing, and also we have a moving averages. So from the plot ACF, we can have a moving average value, and plot PACF, partial autocorrelation function, we can have the aggregated values. Okay, so like in the arima model, in the future stage, we're going to say arima, AR for aggregated, and then I means integrated, which is differencing. If there is no stationarity in our data points, we need to make a differencing, or we need to go for integrating to have our data points in the stationary values. Okay, that we'll see in detail. So these are the plots, you just remember. ACF and PACF are autocorrelation functions as well as partial autocorrelation function to find some values, which is plot the functions to identify whether it is stationary or not. Okay, and from google.colab import files, because from the colab whatever files we have uploaded, that we can list out and upload it directly. Okay, we have just run it again. And how we can upload our CSV file, we already have a cleaned, so that also we can directly upload through our colab coding, like uploaded equal to files dot upload. You can run it and you can upload from here only if you don't want to do from here. See, you just take it and open. I hope you are understanding. Okay, it's going on. Till that we'll go further. So once we have uploaded here, so we have to load our uploaded CSV how through the IO, that is input output. Okay, modules. So import IO, then file name equal to list of uploaded dot keys, means from the listed values of our file name, that we have to list out and we have to upload it. In our DF, we have to read as a CSV, like pd dot read CSV, as you know it. And through from the IO bytes, we can read it from as a parameter IO dot bytes IO dot bytes IO in that uploaded file name. Okay, and then df dot columns is our df dot columns dot we have to strip here. Okay, dots str dot strip, it is just to remove the white spaces if there is any spaces no, in between the columns. Okay, because of the CSV file, there are sometimes there will be more number of spaces, that we can remove the white spaces by using a str dot strip function. Okay, then we already done in the last first stage, that is converting into date time format. But once again, if you want, you can just check it like this. Df of date equal to pd dot to underscore date time of df of date, which is a column, and errors equal to coerce. Okay, this is for method to make it in the format. Okay, then we'll set the index as our date now, because with respect to time series based we have to move, so we'll keep our index as a date. Okay, df equal to df dot set index of date, and then we'll just print first head, first five values. See, we are going for date as an index now. We have ID, product code, and warehouse, product category, order demand, open, promo, state holiday, school holiday, petrol price. We already gone through our data set, which is the petrol demand data. Through that we are forecasting order demand, because how many forecast volumes will be there in the next future days, weeks, and the year. That is our project. So, okay, let's see next how we can extract the time based features. Time based feature means we have a date, right? Through that, how we can extract only year, how we can extract only month, how we can extract only day, how we can extract whether is weekend or not. Okay, and how we can extract that is a quarter wise. Okay, that will check it. So we'll first extract that. See, while extracting directly takes it, this is our date, right? So from that it is showing just year. See, 2024, and month is 1. Okay, day of week 2. Okay, and is weekend, no, 0 means no, quarter, yes, first quarter, like that. Okay, if you just go for next head of 20, no, you can easily analyze. So let's check it once again. See here, it go on changes. See here, 3, 1, 2, 3. Base wise month, gone changing is weekend or not. Okay, and this also quarter. Okay, so that's a way of analyzing the things. And then we have important features like a lag or rolling features. Lag means we'll make it as a list of lags like 1, 7, 14, 30. Let me tell you that 1 means last lag, previous value lag we are taking as a present lag, and 7 means last 7 days lag we are taking as a mean of that 7 days, and 14 means last 14 days lag, mean average value of a 14 days previous we are taking as a lags for the present one. Okay, for 30 means last 30 days, whatever value we have, that average we are taking as a mean as a lags. Okay, and then we'll make a code like that for lag in lags. Okay, df of f of lag is equal to df of order demand and dot shift of lag. Okay, we are making this lag as a shift of previous lags like 1, 7, 14, 30. Like that we are generally taking 2, 3. Okay, and we are defining as df of rolling 7 equal to df of order demand. Okay, we are taking with respect to the df of order demand. Okay, dot rolling we have already taken here, and that is of 7 dot mean. Okay, from 7 mean it is a rolling 7. Okay, rolling 30 is rolling 30. Okay, wm means we can say it is exponentially moving average. So everything I have written here. So this is a main feature to capture the past trends, like a shift function generates a lag features like 1 lag, 1 lag 7 means previous 7 values, previous 14 values, like that, and store demand values from the previous 1, 7, 14, 30 days. Like it helps the model to understand the patterns, how last 7 days values, how last 14 days values, like that. And the rolling function computes 7 days, 30-day moving averages and smoothing short-term fluctuations and also highlighting the trends. Okay, and EWM means it is nothing but exponentially weighted moving average over 7 days. Okay, and giving more weight to recent observation for capturing the trends. Okay, these features are widely used in time series based forecasting models to improve the efficiency in the predictions. Okay, I hope this is clear. Then we'll go for the ADF test. ADF test is augmented Dickey-Fuller test. As I said, this test is important to check order demand time series using the this ADF test. Through that, we can have a standard stationarity test. Okay, first it selects the order demand columns as a series to analyze and removes the missing values. Okay, see here, series we are considering as DF of order demand, and we'll call that AD Fuller method with a series dot drop NA. Series drop NA means we are analyzing and removes any missing values. Okay, then AD Fuller functions calculates the ADF statistics and corresponding p value. P means probability value. Okay, so this p value is very important to check the stationarity. We'll make the condition as ADF results of 1 is greater than 0.05. If it is greater than 0.05, it is comes under the non-stationarity, and differencing is required. Differencing means integrating is required. Differencing means shifting by previous values, like that. Okay, and as I said, so before applying for the building the model, no, like arima model, we have to check this crucial thing whether the data points are stationary or not. Okay, so let's execute and check this. Just a minute, it is loading. So we have made this as run. So ADF test, it is giving ADF statistics, that is minus 82.89. Okay, but p value is zero point 0, means it is lesser than 0.05, means all are stationary. If not stationary, no, we have to go on differencing that. Okay, so that is also simple, that I'll make another one video for separately how we can make differencing and also separate one video for that. But here it is not required now, so it is just showing it's accurate, everything is stationary. We can go for next seasonal decomposition. Seasonal decomposition, I'll make a period as a 365, like a days. 365 means 1 year. If length of series is greater than 2 into 365, else we can make it as a 30. Okay, 30 means 1 month. This is a period we'll take, and Result will take it as a seasonal decompose of series dot drop na if any missing values. Then model make it as additive. Additive wise we are taking the decomposition method and period equal to whatever period we have taken. And we'll just plot and we'll check it. See. Order demand, it has this type of year wise, first month, second month, 3 month, 4 month. This order demand, it is going this way, and trend, see, it is going up and down, little bit going up and down, up down, up down. So there is a trend in that. Yes. And seasonal wise, see, seasonal some way are it is showing repeated type of fluctuation. So this is a repeated cycle is going on somewhere, isn't it? So see, this is up, similar way this up, similar way this up, and similar way this down, and this down, like that. So there is a seasonality, and residual means somewhat errors will be there. So these points we can cancel. So this code performs a seasonal decomposition on the order demand series, splitting into trend, seasonal, residual components. Better to understand the patterns. Okay, here making the period of 365 days, which is for 1 year for the long data set, or 30 days for the shorter ones. Okay, then we'll go for ACF and PACF plots. As I said, autocorrelation function, and PACF is partial autocorrelation function. So we can plot as a plot underscore ACF in the series drop NA and lags equal to 40, means last 40. Okay, similar way for the PACF. Okay, just we'll execute. So method we are taking YWM. So let's check now how it is shows. To show PLT dot show, this is from the matplotlib. See, autocorrelation, it is going very smooth, and also partial correlations. Okay, because it's almost everything is stationarity. Okay, so this is about what we can say uh, on the plot of order demand. It shows how current values are correlated with the past values. Okay, it's almost constant here. This plots helps to identify patterns and decide appropriate parameter like a P and Q while building the next time series ARIMA model, SARIMA model. As I said, P is a aggregated value, auto regression values, and Q is a moving average value. Through this, P value can be found out by the PACF, and Q can be found out by the autocorrelations. So the lags on the particular key cut on that particular value, we can consider that, but it's just a visualization. We can use this with the method also, that we'll see in the next stage. And at the end we can save into some petrol feature stage 2 as just df.2 csv. Okay, so just save it like a df.2 csv and make it index equal to true, and files dot download, you just execute. See, it is downloaded now here. See, like that also you can make it. Okay, so this is how simple second stage of petrol demand forecasting, feature engineering and visualizations. I hope you understand, and we'll meet you in the next stage soon in our playlist of our demand forecasting project, which is very important end to end data science project. Keep watching, don't miss the next video.